Hey everybody, welcome to Western Washington University here in Bellingham, Washington, almost to the Canadian border. We're here to visit with pioneering geologist Myrl Beck, the father of Baja BC. I get asked regularly, are there any modern day equivalents to J. Harlan Brett's, someone who spent his whole career putting evidence together and not many people believing him? My answer is Myrl Beck. Let's go to his backyard here in Bellingham, see what Myrl's got to say. For those unfamiliar with the concept, granitic rock from Mount Stewart in the Stewart Range was studied very carefully by Merle and his graduate student Linda, and they published a paper in 1972 proposing that this whole mountain worth of granite formed down in Baja, Mexico, and was moved almost 2,000 miles to get up to central Washington, along strike-slip faults between 85 and 55 million years ago, Baja BC. So therefore, it doesn't mean that we're just viewing central Washington differently. We're viewing much of the American West tectonically differently after that concept of Baja BC. Thanks for joining us. I think we need to go talk to Merle, don't you? Let's do it. And let's start with your arrival in Bellingham. What year did you arrive here at Western?
1969.
And were you brought in to do some specific things for the department, or did that evolve kind of over the years?
I was brought in to set up a geophysics subdivision of the program. And it did evolve into a much bigger thing than I thought it would be.
Sure.
Because of the paleomagnetism aspect.
Which was on your brain as soon as you hit town here in Bellingham?
Oh, had been for years.
Well, that's what I'm curious about. How did you get into the paleomagnetic world? Who trained you, and what kind of rocks were you working with initially?
I have a long and checkered career. This might take a little while, but
okay, I got time.
Okay. So I started college at Caltech to be a physicist, ended up getting an economics degree from Stanford, was drafted.
Okay.
While I was in the Army over in Germany, I decided I really did want to be a geologist. My whole family on my mother's side was from Cripple Creek, and they were mining people, and so I'd always heard about geology.
Sure.
So I got back into Stanford as a graduate student in geology.
What year are we talking now?
That would have been 57.
Okay.
And I took a course from a man named George Thompson, who was a very great teacher. And one of the things he talked about was the beginning of this new wrinkle that was called paleomagnetism. And I thought it sounded really neat. So I did my master's thesis in that. And then I went to work for an oil company for a year, and then fortunately I was hired by the U.S. Geological Survey to run what they called a rock magnetism lab in Washington, D.C. And I worked for them for 5 years, running this lab, doing field work, doing, what we called pole position paleomagnetism.
Sure.
Measure the rocks, find out what the direction is.
And which rocks were those? Where?
Oh, it was mainly in the Appalachians.
Okay.
And also in the Great Lakes area, the Keweenaw basalts.
Okay.
And the Duluth-Gabbro.
Oh, wow. Okay.
Duluth-Gabbro ended up being my PhD thesis.
Okay.
Anyway, I worked for them for 5 years, and I frankly hated it in BC, DC. And I wanted to get back west.
Sure.
And they wouldn't transfer me. And the people that got transferred could do so by threatening to go to work for a college. And I couldn't do that because I didn't have a PhD. So I applied at UC Riverside for a PhD program. And the reason I chose that was largely because my father had just died. My mother lived within commuting distance. I had a wife and 3 kids.
Sure.
So they accepted me, and I finished my PhD really quickly and came up here. My PhD was, as I say, the Duluth-Gabbro, which I done the field work while I was working for the survey. when I got here, I knew that's what I wanted to do. And so I wrote an NSF proposal, and got laboratory equipment, and started working.
Okay. Well, during your undergrad, your master's, and your PhD, we're in the 1950s through the 1960s, off and on then. How much is plate tectonics part of the discussion? Can you characterize how the paleomag work was intersecting with tectonics, if at all?
Oh my God, it was very important. As you're no doubt aware, and your listeners are probably aware,
Sure.
the main evidence for plate motion, the original stuff, was the Vine and Matthews magnetic anomaly strips. But that involved magnetism, and it involved reversals of the Earth's magnetic field. Well, at the same time, in England, mainly in England, people were working on what pole position paleomagnetism. And they would work out where the pole was with reference to Europe in say, the early Tertiary and the Cretaceous and the Jurassic and so forth. And the same thing was going on in North America.
Okay.
And if if North America and Europe had not moved with respect to one another, those polar wander curves should have substantially coincided, but they didn't. They were obviously displaced, and in such a way as to second the notion that North America and Europe had been sliding apart. And that was exciting, and lots of people started doing paleomagnetism then. And they discovered that it was true of all the continental blocks. Australia had its own curve that did not match with India, and India didn't match with Central Asia, and so forth and so on. It became clear from this lack of coincidence of paleomagnetic poles that the continents carrying the rocks on them had moved with respect to one another. And it became really hard not to believe in continental drift, as we called it then.
Sure.
Plate tectonics now. It really became hard not to believe that. Some people managed to do it.
So here's Myrl Beck and Linda Nosen, January 1972. We're coming up on 50 years.
Jesus, is it that long? Oh my God. Oh Lord, you're right.
Anomalous paleolatitudes in Cretaceous granitic rocks. We describe anomalously low paleomagnetic inclinations in radiometrically dated batholithic rocks exposed in the Cascade Range of central Washington. Our results suggest that these rocks originated roughly 25 degrees further from the Cretaceous pole than their present location. A simple application of plate tectonics based on existing models can tentatively account for our results. Alternative explanations seem unlikely. I like that last sentence.
Yeah, and I've stuck with that ever since.
So, what was the context of that paper? Were you adding to somebody's idea already, or were you coming out of the blue?
No, I was adding to an idea that I had originally originated in my brain some years earlier.
Okay.
But I was also basing it on some results that other people had had essentially at that same time.
Okay.
And the context is, when I was at UC Riverside, I had already, I actually had more publications than a lot of the faculty. And I had a friend there who wanted to do paleomagnetism. And I had a functional lab going in Washington, D.C. So he and I studied the paleomagnetism of granitic rocks, which we called the Southern California batholith.
Okay.
Now I think they call it the Peninsular Range batholith.
Yeah, give us a couple examples. Where could you find those rocks that you were looking at?
Near San Diego and on the, well, we didn't go into Mexico, but
okay.
Northern Mexico, around Riverside, San Bernardino.
Okay.
Wherever there's granitic rocks exposed in the mountain range, that's that batholith.
Got it.
And we did a pretty thorough study, And Ron went and made the measurements at another guy's lab. Ron was my student, my fellow student.
Sure.
And we got a really nice paleomagnetic direction, but it didn't match the reference pole. And the way you looked at it, it looked like it had been, these rocks had originated south of where they are now and had rotated clockwise. And so Ron and I puzzled over that. And at about that same time, there was a very seminal paper published in GSA Bulletin by Tanya Atwater, of whom you've no doubt heard.
Yep.
And she likened Western North America, when she really got waving her arms, she likened Western North America to a huge dextral shear zone. And so Ron and I sit there and say, well, what happens if our little chunk of batholith is stuck in the shear zone? And so the answer, of course, is with respect to the internal part of the continent, outside the shear zone, those rocks will have seemed to have been moved north and rotated clockwise. But we didn't publish that.
Okay.
It was too revolutionary.
That was in the mid-1960s, maybe?
That would have been 67, 68.
Okay.
So then I came up here and I got in my lab and I ratted around trying to find good places to work.
Yeah.
And I got a bunch of grad students, and one of them was this very nice and an intelligent woman named Linda Lawrence, who later married and became Nosen.
Okay. And
Linda and I worked on my God, what granitic rocks are there around here better than the Mount Stewart batholith? You can drive right through parts of it. You can go up Icicle Creek.
Yeah.
And so we went up there and we sampled in 8, 9, 10 places and drilled standard paleomagnetic sites, 6, 8, 10 cores per site, and brought them down here. And she worked in my new lab and she got a beautiful direction. And lo and behold, it looked like these rocks had moved north with respect to North America and rotated clockwise. And I said, my God, that's what Tessera and I found. At that point, I started thinking there was something really seriously going on here. This kind of application of paleomagnetism to tectonics was pretty much unheard of. It was ignored by most geologists, but I think the paleomagnetic community took notice.
Now, a decade earlier, the paleomagnetic stuff of Vine and Matthews was celebrated, right? So there was some acceptance of paleomag, but yet this was somehow different?
It's quite different in that the Vine and Matthews hypothesis was based just on the notion that the magnetic field had changed direction, polarity.
Yeah.
We were talking about the changes in the direction of the magnetism locked in rocks, and it's quite different.
Yeah, yeah.
What they were talking about was simple. We were talking about something that had a lot more oomph to it somehow. So anyway, I think a whole lot of paleomagnetists thought that was really pretty interesting. And at the same time, there had been 2 other papers published that also didn't get too much publicity. One of them was by Ted Irving and some people. Ted Irving is probably one of the absolute fathers of paleomagnetism. He died a few years ago. He was an Englishman who worked on Vancouver Island. And Ted had found that there was some really strange results in Cretaceous rocks on Vancouver Island. He was working with paleomagnetically not particularly nice sedimentary rocks and complicated things, and we didn't have the laboratory facilities in those days to measure a whole lot of things. But Ted's conclusion was it looked like things had moved with respect to the inside of the continent.
Right.
At the same time, a guy named Packer, was it Packer? Yeah, and some graduate students up in Alaska had found some volcanic rocks that looked like they had got magnetized way south of where they were now. And these three things came out at the same time, mine first and the next two.
Yeah.
And I started saying, hey man, there's something here. So I dug into the literature. And the result of that was the American Journal of Science paper, which I don't know whether you've seen it, but that's the one that really, where the stuff hit the fan. Because all the geologists read it, for one thing.
Okay.
And a whole lot of them didn't want to believe it.
Is it this or something else? In the early
No,
80s?
no. Oh no, this comes. Oh, this one is from a Mexican journal. No, you want to look at the American Journal of Science.
Okay.
I'll get you the.
Okay, good.
I'll get you the reference.
So that's the one that broke it to a wider audience, not just the,
much wider audience.
Okay, and what? Okay, so you get a wider audience. So in what form are you getting pushback?
It's really quite interesting. To my way of thinking, most of the geophysical community, especially the ones who did paleomagnetism, knew how it worked and could read and understand what I had done in depth, agreed that what I had said was not only true, but that my interpretations were, substantially correct.
Right.
The gray eminences in the geological community just absolutely abhorred the idea. And I'll give you two examples. One was, for the local stuff, there was a guy named Peter Misch, whom you may have heard of,
sure,
who absolutely dominated the geology department at University of Washington. And he was totally revolted by my ideas and was quite scornful of what I said, but not normally to my face, mainly behind my back. So he was the local opposition, but the main opposition was Bill Dickinson. And now, this is my opinion, and a lot of people would disagree with this, but I think that what happened with Bill was brilliant. He was a great stratigrapher, and he had a good grasp of how the early ideas about plate tectonics worked.
Sure.
And Bill had been at Stanford, and Bill had worked on a model for how the West Coast developed tectonically. And he finished the model, and he was, I've done it, nothing more to do. So he moved to Arizona and started working on other things. Well, then myself and Ted Irving and other paleomagnetists came along. Bill's idea basically was plate motions were orthogonal. They're like this, or like that, or they're like that. And he had never really considered the notion of oblique extension and oblique compression. And he had also didn't know anything about the Kula plate.
Yeah.
He should have, because Tanya Water had already said that shown that it existed. But, well, nobody knew where it was 100 million years ago, or even that it existed at that time. So anyway, Bill, frankly, didn't want his model to be disturbed. And so when I came out with the stuff, he was vehemently opposed, which, let me interject right now,
please,
before I forget to do it. I did not name Baja BC.
I was going to ask. Yeah.
It was Ted Irving.
It was.
Yeah. And I actually never really bought into it, because his idea was the whole thing moved as one big chunk.
Okay.
And I thought that things moved in separate littler chunks. But it was the same thing. South to north motion and clockwise rotation.
So when you hear you're the father of Baja BC, you kind of wince just slightly, because it's not quite the concept that you were.
I actually argued with Ted after he brought that out, but he was such a articulate guy.
Yeah.
I mean, you don't argue with Ted.
Well, it was catchy, I'll tell you that. And it grabs people's attention, of course, more than some other kind of more vague way to describe the translation.
And I'd say, but Ted, the differences between the various units are so great. And he'd say, we're just playing with it. We're just playing with it. Oh, what a guy.
Well,
So, anyway, we had a real simple model. We would look at rocks from Baja BC, and they would all, their paleomagnetic direction would be displaced in such a way that their paleomagnetic poles would be over here with respect to the reference pole. And they'd all be over here. And we had a real simple explanation for it. They'd all moved in the same way. If you want to account for these aberrant directions without this motion, you've got to invoke all kinds of things. Tilt here, and remagnetization there, and age problems there, and flattening of inclination here. And then you have to explain how all of them came up with results that look like everything had moved in the same direction.
Right.
If a geologist says, if I say to a geologist, this piece of rock has moved up here with respect to that piece of rock, he's going to look for a fault. And we didn't have any really big faults. And there's lots of reasons for that. Partly because there weren't any really one big fault. There are a whole lot of little ones.
Right.
Partly a lot of it's been covered by plateau basalts, that kind of stuff.
So this is a rare opportunity for folks who like the idea, but they have immediate questions. This is a great opportunity for them to hear from the horse's mouth. One is, well, wait a minute, how can you say anything about the paleomagnetic history, because there's been changes in the location of magnetic north, for instance? How can you factor in this wandering pole business? Is there a simple way to describe how you deal with that?
I think, I'm not so sure how simple it is, but I can deal with it.
Okay.
When we say that the Mount Stuart batholith has a pole that's displaced from the reference pole, what we're saying is effectively this. Well, first of all, let me go back.
Sure.
Yeah, the pole moves around, but the magnetic pole.
Right.
The magnetic pole has essentially always stuck close to the geographic pole. It precesses around it. And sometimes it's exactly there, but usually it's 5, 10, 15 degrees away. So if you were to look at just the magnetism of a single rock at a single moment and and calculate a pole from that, it wouldn't be the geographic pole.
Right.
It'd be a few degrees apart. But we don't do it that way. What we do is we average over a long time period. So the notion is that the magnetic pole wobbles more or less randomly around the geographic pole, and if we average all that, we'll get essentially a pretty damn good estimate of where the geographic pole was. So, okay, now we go to, we're mostly interested in sort of late mid-Cretaceous rocks here. All through the central part of North America and into the Appalachians, people have done paleomagnetic studies of rocks of that age. And they've done it properly, averaged out we call that the secular variation. Average that out and get a direction that should tell them where the pole was with respect to that rock. And they plot it on a map. And if you do it in Kansas, and you do it in Louisiana, and you do it in New Hampshire, you get pretty much the same place.
Yes.
In fact, quite a tight grouping, which we call that the reference pole. Okay, so now we know where, with respect to North America, the pole was, and so from that, we should be able to calculate what the magnetic direction should be in any place on the continent. We call that the expected direction. So what I'm saying is that throughout the Craton and the younger rocks in the Appalachians, the expected direction and the observed direction are almost the same, but on the West Coast they never are. And the West Coast, the way they're different is they have a shallower inclination and seem to have been rotated clockwise. And that's exactly what you'd get if you had a block of rock that was stuck in a dextral shear zone, being carried north with respect to North America and rotated clockwise. And that's the story.
And that's not the first time you've given that explanation, because you've been trying to answer reactions for the last 50 years, essentially, from geologists and non-geologists alike, right? That's
entirely true. It actually, Nick, got kind of tiresome and led me to stop working in the Cordillera. I don't know whether you know that I spent 20 years working or 15 years working in the Andes.
I did not know that.
Yeah, and I also worked in the Caribbean and I worked in the Aegean. And each place I found, different patterns. The Andes of Chile and Peru are a really great example, because there, if you can visualize, if we had a black chalkboard I would draw it, but I can't. You can visualize, look at a map of South America in your head, and you can see that that Peru comes down from northwest to southeast, and then in Chile it goes due south.
Yep.
And subducting into that wedge there is the Nazca Plate. Mm-hmm. And the Nazca Plate is affecting the coastal rocks in both Peru and Chile. And we get a pattern, but it's not like the North American Cordillera. Mm-hmm. What we get is in Peru, the rocks are rotated clockwise, but pretty much stayed in place. And in Chile, the rocks are counterclockwise,
yep.
Excuse me.
Yep.
And in Chile, they're rotated the other way.
Okay.
But they haven't moved. Why haven't they moved? They haven't any place to go. You can't push them up into more continental crust.
Yeah.
And so I thought that was an important observation, that North America and South America, even though they've undergone what they used to call Andean tectonics, have an entirely different paleomagnetic signature.
Interesting.
And I believe that it's mainly, you could just boil it down to the shape of the continental margin, or the plate margin.
So in part you left North America because it was getting tiresome. You felt like you'd laid out some pretty impressive evidence, and you get all this pushback, but is part of the reason you left to get more context for western margin of the Americas? And it was almost another way.
A bunch of reasons. One reason is that everybody and their uncle was working on Cordillera and rocks at that time, because we'd opened up, we and Ted and I and Alan Cox down in Stanford had opened up the whole thing, and so everybody was working there, and there wasn't any rocks left for me to work on. And secondly, I could get funding for South America more easily than I could get funding for North America, because I didn't have target rocks to work on. And thirdly, it was because I wanted to see whether the results from Chile and Peru would match what we got up here. I'm sure glad I went down there.
Good. Well, talking to you, especially you just mentioning that you left the Cordillera in North America after doing a bunch of work, brings to mind J. Harlan Bretz. And I don't know if you're comfortable mentioning him in this conversation, but I've been doing a fair amount with Bretz and his rather intense work in the 1920s in eastern Washington. And then at some point he says, look, there's nothing more I can do. I've laid this all out. You're not going to come look at these places. I'll just go back east and start looking at caves and stuff like that, and just kind of. And of course, he spent much of the rest of his life not being recognized for that important work. Are you wanting to go here at all with parallels?
Not really.
Okay.
Brett's story is much more was much more pathetic than mine. I mean, nobody has ever said I was stupid, and the community hasn't, locked arms and expelled me. Mm-hmm. I've had a lot of support over the years. Sometimes it's a little frustrating that people are so desperate to disprove what I've shown, what I assume I've shown,
yes,
rather than go out and look for evidence as how it happened or why it happened or, that sort of thing. I was a little discouraged by the old zircon work. The early zircon work purported to show that all the rocks here had always been here, and apparently now they don't. Now it shows the opposite.
That there's more and more good evidence lately that they're on board with you.
But it hurts. It almost hurts my feelings that people are so anxious to prove that what I said was wrong that they devote half their life to it.
Do you have pet ideas for why that is? Is this human nature? Is this some sort of clannishness among scientists? I mean, we're supposed to think independently and not have all this baggage, but...
Nick, if I answered that question, I might end up insulting a bunch of people that I'd like to regard as friends.
Right. Well, I'm guessing folks that are watching have learned on their own about Baja BC, and they're aware of some of these new developments in the last 10 years from many different points of view. The zircon now, the ammonite fossils, the new way to look at the Swakane gneiss and see connections with Southern California. Mm-hmm. So is that message getting to you? Are you say you're not keeping up on the latest developments? Are you aware of this growing movement to find different ways of evidence that support your original work 50 years ago?
Well, I'm vaguely aware of it, partly through you.
Okay.
I have friends who are still working in the field.
Yeah.
There's a woman at Western named Elizabeth Shermer. She's basically into tectonics. Mm-hmm. And I have a beer with her now and then, and she more or less tells me what's going on.
Yeah.
I see Ray Wells every once in a while. But no, people haven't really, I haven't made an effort to keep up, and I'll tell you why. And you may want to scrub this part, but
we'll try it.
My wife died of ovarian cancer 9 years ago. At that time, I was still doing a little bit of research, but not much. And that was such a cruel death that it made me want to do something about ovarian cancer research. Mm-hmm. And so I started volunteering at Fred Hutch down in Seattle. But the organization that I was volunteering, the program collapsed. And I started writing that blog that you know about.
Yeah.
And if I study anything at all now, it's ovarian cancer.
Interesting.
I'm still interested in. I wish Ray Wells would come and sit on my deck and tell me what he thinks now. Mm-hmm. The ideas of how this came about seem to have changed to somewhat from what I envisaged.
Yeah.
But the general result seems to be the same.
Well, that's the amazing thing. We're 50 years later, and the evidence continues to pour in, as far as I can tell, all in support. I mean, there's a growing tide. You should know about all that.
Yeah.
You don't.
Well, I wish that some of the other guys that had involved in it were still alive. Alan Cox, of course, died many years ago. And Ted died just a couple of years ago.
Is that part of this at all?
That might have been part of the problem. Maybe early on getting grant money.
Yeah.
But after I'd published a few papers and got to be everybody's favorite kicking boy, I had no trouble getting funded. Uh-huh. The reason I came here is I wanted to be on the West Coast. Mm-hmm. I got my PhD, and there were only two Okay, and I was going to go back to the USGS, but since I'd gone to all this trouble to get a PhD,
Yeah.
I decided I'd try to teach someplace. And there were only 2 jobs at that time on the West Coast. One was at San Diego State, and one was here. And I interviewed in both places, and both places offered me jobs. And I chose this place because the teaching load was less, so I knew I'd have more time to do research. And there was the North Cascades right over there. And if there's anything I love to do and I would still be doing it if I could,
Yeah.
is rat around in the mountains. Those mountains probably played as big a role as anything. So no, I think at first maybe people would say, well, hell, he's from some podunk place back out of nowhere, so who needs to pay any attention to him? But that didn't last long.
Good.
And since then, I don't think it's been any problem.
You feeling okay? Want to do a couple more? Okay. Back to the common reaction I get when I share your message, and one is the polar wander thing, another is, well, how about folding of the rocks? Or it's been a long time, since 60 million years. How can you assume that those inclinations are the way they were when that magnetite froze in place?
Yeah, right. Okay, that's one of the principal alternative explanations for these strange directions. As far as layered rocks that are folded, that's no problem, because we can graphically unfold them. We can rotate the direction to what they'd be if the rocks were flat. The main problem has been with the batholithic rocks. The Peninsula Range batholith would be one.
Yeah.
Mount Stewart, obviously, and some other stuff that Ted Irving worked on in BC. With the batholithic rock, you have no evidence of the paleohorizontal, so you have to infer whether or not it's been tilted. Well, that was true until not that long ago, when some real smart guys back in Princeton, I can't remember their names now, developed a method of determining paleobathymetry. So let's assume that the Stewart batholith had been tilted. So it got magnetized and it got tilted, and then it got planed off at the top here. Well, if you sampled it at the top, you would find evidence of how deep that rock had formed. And if it had been tilted, it would show. Part would appear to be shallower and part deeper. I'm garbling this, but
No, you're good.
hopefully
You're good.
your watchers will understand.
They will.
But these guys in Princeton sampled all over the Stewart batholith, and they got bathymetry that showed that it hadn't been tilted. And the evidence for its tilt comes from some older rocks that are tilted. I can't remember the name of the formation. They're on the east side, I think. And but they're faulted against them.
Yeah.
So they don't actually apply. But that is one of the objections, is if you're going to deal with a rock that has been tilted, if you're going to deal with a rock that has no evidence of paleohorizontal, you always have to wrestle with the question of, is it still in place or has it been tilted in some direction? One of the things that comes out of the Cordillera and paleomagnetic work now after all these years is that if these batholiths are all tilted, they're all tilted the same way. They're all tilted down to the southwest. And while that's not impossible, it seems unlikely.
Sure does.
But with the other rocks, which Ted worked on a lot, the layered rocks, as I recall, they have evidence of bedding, and so you can just correct for that. That's pretty routine in paleomag.
Good.
I don't think anybody's doing that kind of stuff anymore. My God, every likely outcrop on the west coast has got drill holes in it by now.
Well, this one somehow managed to escape your drill holes. I don't know how we figured that one out, but
it's a beautiful chunk of rock.
Looks like an old friend of yours.
Mm-hmm. I had a few important people who were enraged by what I was proposing, but I didn't think I was ever treated badly or anything like that. I think people like Bretz and Wegener got a lot more opprobrium than I never got any opprobrium. You might try talking to Ray Wells of the USGS. He's a younger guy.
Mm-hmm.
And the ideas that I would like to say that I started have evolved.
Yes.
I started along with Tanya Atwater.
Mm-hmm.
And Ray is probably the one who knows how they've evolved best of all. You might want to talk to him.
I will. He just retired.
He did?
Believe it or not.
All these children retiring.
Well, you brought up Tanya a couple of times, and she's obviously a very important figure in developing kind of Western North America tectonics, and that's an understatement. Where was she with your work, or were you in different universes?
She's the one that realized that this oblique behavior between first the Farallon plate and then the Pacific plate would have the effect of making a big shear zone.
Yeah.
And that alone is enough of a contribution to geotectonics to put her in the National Academy, which is where she is.
Yeah. Yeah. Maybe if they see this.
I should probably not say this, but I would really like to be elected to the National Academy of Sciences. And I shouldn't have said that, because that queers it right there.
No.
But there are only a few paleomagnetists in there. One of them is Ted, and he's dead.
Mm-hmm.
I think there's only one other, and that's Neil Opdyke, who was one of the founding fathers in a sense. Well, he was more like me.
Mm-hmm.
He was what did they call it, an elderly nephew?
Yeah. You did say that, yeah.
Yeah.
That was good.
But Neil's still alive, but
Mm-hmm.
he's older than me. He's living in Florida and trying to avoid coronavirus, I imagine. So yeah, no, I don't really need it. I mean, I'm perfectly content with life. But if anybody wants to elect me to the National Academy, I would not say no. What a joke.
Thanks, everybody. Hope you enjoyed that visit with Merle. Gives you a little backstory on the Baja BC concept and the father of the whole thing, Myrl Beck. Thanks for joining us. I love you. We'll look for you next time. Goodbye.